Hello everyone. Sorry for joining this late. I had some internet issues on my end, so that's why. Just give me 2 minutes and I'll set up my screen. Okay. So I guess we can just start. People will join. It's like in some time they can have a look at the lecture, recorded lecture. Okay. Let me give you all your permissions. Hmm, Yeah, set. Okay, so this is likely our last week. We'll also have an extra session tomorrow, and that in that extra session for now, I'm thinking I'll cover up some of the clustering methods for hierarchical. The last two lectures of week 12. I haven't covered it today because I thought it would be too much for a week. And apart from that, I was thinking some is like we'll cover all of the basics of Python that we did till now, say from t-test and all. So just a glimpse of all, and we'll also share that Py notebook with all of you so that everything is in one corner and you don't have to go again and again to the loops to see okay which thing to do what. We'll also, while doing the session, we'll do something as where you can do with me and we'll have some problems. Okay, how do you do this? What would be the probability mass function for this function or something like that? And so that you can also get a glimpse of it. I'll try to have some examples with me. If not, we can always try the example problems that are there in the website also. I have a couple of examples from the book that Dr. Ramesh has guided. So we'll look into it, but probably it's a day of time for me also to prepare. So I'll see what maximum I can do. So accordingly, for you guys to prepare for your exam, that's ahead. Okay. So last week also we were looking at clustering. After ROC, we saw different types of clustering into which we went into supervised and unsupervised. And we didn't actually go much into it, but we did saw some standardization of the data set. For clustering again, so we saw different two types of clustering. One was for k-means, another is here. So now, so if any one of you might remember, so apart from hierarchical, was what was the other class for clustering? So hierarchical is one such. What was the another one that was there for week 11? It's like the different parts of clustering or something like that. When clustering actually started with. Any idea? Or do you all it's like just forgot about it or have some glimpse about it that okay, something was different in it, something's different in this one. We saw okay, so last week was just about to handle the what do you say, the dissimilarities in your data and similarities in your data. But we did saw a flow chart before that. I did made up in my slides also for different types of clusterings. Wait, let me just pull it up. This Yeah, so okay. So at first we just started with the cluster analysis and discriminant analysis, where one was supervised, another was unsupervised, where we didn't give any information to it, and it was viable to all of the data sets that we have. After that, the second one that we had was about Location. Okay, well, you can always go back and look at it. So we saw different distances through which you can compute your cluster within for. But after that, in week 11, we directly had k-means and different. So I guess we did saw a flowchart for it, if I'm remembering correctly. Handling missing data. Uh, any one of you remembers? What was the other one? This is for different variables. I guess it was all about of the different types of distances only and not based on this. Okay. Yeah, yes. So it was one was your part, so where K means was a part of that. So it was something as we had our clustering methods. I guess someone's trying to join. Let me join that person. Yes, so we had this clustering methods, and part of those clustering methods, one where we remember k-means was there, but this method was nothing but partitioning, where you partition the two of your data set and based on it you classify it or you make a cluster. Another is like something as hierarchical. That we'll just see today what this hierarchical type is. Now, based on this hierarchical types, what you see is spelling might be off. Okay. What you see is like how the data is hierarchical, is like based on which type of approaches. So one such approach that we'll see today and is like tomorrow would one is agglomerative and another is divisive. Okay, divisive or decisive, it's something like that. Okay. So we'll see the spelling. Okay. So only difference in between them is one has a purpose or approach as it will merge data set. So it is like bottoms up approach. Another one is like top down approach, which does is like it will consider everything as one and then it will start splitting things one into another, one into another. It will terminate till the point that all of its conditions or handles has been proven right or correct, and after that it will the loop would be done or your clustering would be done. So then it satisfies that okay, all of the conditions are done. So these were the two differences or two methods that we had. Based on that, one also says that okay, one is supervised and another is unsupervised, something like that, where priorly you have some information about your data set, you know the ground truth about it, and that is where your k-means lies. Whereas the another one, you directly assume that okay, all of the data set is something like that. But there also, this data set, as we previously saw, is very sensitive towards the number of clusters that you give. So the number of clusters, if you have, let's say two, it will try and classify your data set accordingly. Whereas if it's like three and four, then it will also start seeing differences in between them. If it's two and it sees that okay, all of the centers are nearby and the centers have been sufficed, so okay, no need for me to further classify them or no need for me to further check in between points and points, then it will stop there itself. But if you keep on increasing the number of clusters, it might also be possible that after a certain point, it would consider each and every independent point as one specific cluster. So this kind of hierarchical techniques are very specific to the number of clusters that you want in your data set. But that number would always depend upon your choice of research question. Okay, are you trying to differentiate in between things? Are you trying to see if this particular risk is like is safer or not, has a risk or not, investments or something like that, or okay, would it rain or it won't rain? So if your model is something like that, you can choose to have a number of values there. But let's say if you're trying to differentiate, let's say a score of people in between three classes, class A, B, C, or division A, B, C, and in between them you want to see okay, which class performed better or which class scores were within which particular gradient or something like that. Based on that, you can have your number of clusters accordingly. So it always depends on the question, it's never random. So there are scores that what I told you in last class, one was the Silhouette score that I spoke of. So this, if you forgot, you can always go around Google it. So this is a kind of cluster score. Now in the Sulhauter score, what people do is like they'll say that okay, if the cluster different discrimination, the if different clusters that have been made and if there's a plane of separation between both of them, so it will give you a value as greater than 0.5. If the value is greater than 0.5, let's say if the value is even greater than 0.7 or 0.8, it says that okay, there is a better discrimination in between the data sets that you have given, whether it's two cluster, three cluster, or more than it. Okay, so there you can have a chance to compute it. But let's say in cases where you have, let's say, only a 1D data set, you no longer now have any 2D data sets. So in such cases, what you can do is like you consider all of the data set as one, and then you try and do this kind of approaches, where in those cases, this divisive one or decisive one, whatever it is, we'll see. So that approach is very it's like reliable in a way that you first consider that all of your data set belongs to one specific group, which is very true for your case where you only have a 1D data set. Then you try and it's like split it into groups and groups and groups. When you do that, you will be get a perfect classification. Now that kind of thing where what you do is something called as a dendrogram. Okay, so this is like just brief about what the entire is like thing that we'll look into today. Okay, so we'll just look into differences in between both of them. This, if you all might have read, so okay, I just told you that this can be classified as being as one is agglomerative, another is okay divisive. It is divisive. The first one is a bottoms up approach, which is nothing but it will keep on merging. Okay, so it starts with each object and it will form a separate group. Whereas the another one is a divisive approach, which is a top down approach. It will start from top and it will consider everything as one, and then it will start splitting it on it. So let's say if I have made one particular string, in between them it will split now. Again, we have two, then in between them it will split again. So it will keep on splitting against till the point where the number of clusters that you gave suffices or not. And if, let's say, there would be a minimum distance in between the clusters, there would be a maximum distance in between the clusters, or there's no difference, so they are barely separated, till the point that all of these things are nothing but sufficed. Okay. So these techniques are good. You can always do your classification. You can always do your clustering based on them. But only issue with these techniques is the thing that is done. Once it's done, it can never be undone. In a way that this won't take much of the time to run in your computer. It's like it won't take much of the power, or the computational cost for it is very less. So it won't take that much time to run, but it's also good for smaller data set. Okay. So also it's better for a smaller data set. If it's a bigger data set, it will take much more time and it will be computationally intensive also. But these techniques cannot correct for the erroneous decision. For example, let's say you thought of taking instead of a group, two groups, you thought of doing it for three groups. Now, now it's done. You cannot change the process in between in a way that, okay, now you might have a counter argument that, okay, all of the methods are something like that. I'll just try it, run it, and then I'll do it again. But sometimes what you do is like, let's say in learning kind of models, you're doing some machine learning or deep learning kind of techniques where your weights are actually affected by these decisions. So based on these decisions, entire all of your algorithm will now change. What you are thinking in the output, now you'll have to go back again and check these weights again. So it's always better to run these kind of techniques for smaller data set, not for larger data sets. Also not to include this type of techniques in networks because it makes the network very heavy. Okay. So yeah, as we saw, one is a bottom-up approach that is agglomerative. What you do is like you keep on merging everything. So you agglomerate everything one by one, as its name suggests. Okay. And then the another one is divisive. It will start on dividing things. So it was one group. Now it will start splitting things into it. Okay. So as we saw, so first is like this is nothing but this is called as Agnes. Agnes is nothing but agglomerative, and this is it stands for nesting. So it will mix all of them. So it will try on merge. It has merged. Okay. Whereas the another one is divisive. So it was nothing, and this is Diana. So this is nothing but divisive analysis. That's it. So these are like some fancy words kept by some people. And then here what you do is like you have a big cluster. Now you keep on dividing that cluster into smaller things. At the end, what you get are all independent random variables. Okay. or your events that you were looking at. So this is just interpretation for both of them. Now there's again one more thing, that is nothing but there are different kinds of linkages for it. Yeah. So what I just told you, this is kind of a structure that is called as dendrogram. So it's basically used to represent the processes of this hierarchical clustering. So what this clustering differences are is like what we just saw. So this is something like a tree. Okay. So you assume there's a bigger tree. Sorry. Yeah, you assume a tree is there. Now when leaves grow, branches grow, you have different, it will go on, start on spreading here and there. Okay. But let's say if there's only a small sample, it's like a small sample of it, and then it is starting growing on, and from that state it will make one, it will make another, within that particular branch it will have something else. So that is why this kind of techniques are something called as tree branch technique. So a layman kind of word to refer to them. So a dendrogram looks something like this. So it first assumes that everything is a one set. So it will have everything as one set based on your type of linkage. What linkage is, I'll just tell you. Based on the type of linkage, it will start differentiating the groups. So this group was essentially one, but then it saw that, okay, these two are different. So it will make them two. But here, what you see is if you have two different data sets in this, as well as if you have two different data sets in this, what you essentially can do is like you can divide this groups based on your differentiation. So this is how dendrogram can also help you do your clustering. Okay. Now, as we saw for k-means, there was still how to score to differentiate or to compare your cluster analysis. For dendrogram also, you have different scores. So there are some correlation scores based on correlation techniques. Based on those correlation techniques, you can see how minimum or how far are how far apart are your data sets or your clusters being placed. So based on those scores, you can also classify how better your discrimination or delineation is. Okay. So yes, this is how it is used to present. This is how it looks like. Yeah. So these are the different distances that we have. So measure of different distances. So one represents the minimum distance here. One is the maximum distance. So for your understanding, this is nothing but your different 2 point of objects within which we'll be looking at the distance. One is the mean for the entire cluster, and another is nothing but the number of points that we have in that particular cluster. Okay. Maximum you can find. Mean distance would be subtraction of both of the points, whereas the average would be you take the number of points in both of them, so take an average of them, and you difference like subtract the point in between them, so basically take a displacement out of it. Okay. So the two things that we just saw, so one is nothing but this one minimum. So minimum would be something like, okay, you have two objects like this, so first boundary, first border. So this is my minimum distance in between both of them. Okay. Now this minimum distance is also called as something as nearest neighbor. So what is written next slide, this is also called as nearest neighbor clustering algorithm. Okay. Now, in this nearest neighbor clustering algorithm, this kind of thing is also called as this single linkage algorithm, where you only connect to this two. Whereas if the another one is like maximum, so in that what you do is like you have this boundary, you compare from this layer to this layer. Okay, so this is your farthest distance. Sorry. So this is your farthest distance. And based on this farthest distance, this is called as complete linkage. So you go around the entire cluster to check the sizes or location of that particular cluster for it to differentiate or for it to check that, okay, where it lies along. Okay. So these are some keywords that you should notice. So for maximum distance, it's the farthest neighbor clustering algorithm. Hence, when there is a maximum distance in between any two clusters, if they exceed that particular threshold that you have, so it is called as complete linkage algorithm. Okay. So these are some keywords that you should know, probably would be asked. So this slide is very important for you to look at. Okay. Another is just an interpretation out of it. If one has not read those values, so just go through these keywords and the sentences might feel boring, but is good for you to understand them. Okay. So this again, this points also that farthest neighbor algorithms, they tend to minimize the increase in the diameter of the cluster. They will tend to minimize the increase at each iteration as little as possible. So they are again trying to check that, okay, if the distance in between them can be increased or not, or decreased or not. Accordingly, if I can make the clusters two separate clusters, or can I make them one also. So if they are two clusters, or rather some compact and approximately equal in size, then the method will produce a high quality clusters. If not, then the output would be meaningless. Okay. After that, okay, choice of measurements. Yeah. So this is how we saw. So this is nothing but taking average of all of them. So this is your first one. This is group average. Nearest neighbor is you take the firstest points. Farthest neighbor is you take the last point of your clusters and you compare both of them. Okay. So based on it, if it's a first type, it's nothing but some ball kind of shapes you'll get. Okay. Where you're trying to average for all of the clusters in between this metric. Whereas the second one, if you just try and look at the only first points, the minimum points that you have, so this will bring you something called as an elongated structure. So something which is like branch like this. Another is nothing but you have your farthest point. So that farthest points here, if you see, this would be nothing but related to like this. Now this farthest points are something like compact, but in this case, you won't be able to separate in between points. So it's always easy way to go with this part with this one, that is nothing but a single linkage instead of a complete linkage, because in terms of complete linkage you might not know that which particular data set is that it is following to. Those might be outliers that you are looking at. So outliers aren't good for your data set or for you to also make your interpretations based on the outliers. That is why I always go with single linkage to begin with, then further based on your data you can tune it accordingly. Okay, so yeah, so here's the main table that you want to have look at. So first is partitioning methods. It will find some mutually exclusive clusters of spherical shape. It is based on distance. The distance matrix we saw, Euclidean. Then we have this Minkowski, and there was also something else as like, what was it? Based on the absolute distances in between both of them. Okay, so here you may also use mean medoid to represent the cluster center, and it is effective for small to medium data sets. Whereas in the hierarchical methods, you have multiple levels of decompositions to make. It cannot correct for the decisions that you made wrong. It may also incorporate another techniques, that is, you can do micro clustering, or you can do consider the objects such as linkages that we just saw. So this kind of linkage is nothing but a method for it to solve. Okay, so based on the method that you are giving, it will solve or make the clusters accordingly. K-means versus hierarchical clustering. So K-means is also part of your this partitioning method, or that is nothing but your supervised one. Okay. So the method assigns record to each cluster to find mutually exclusive cluster based on the distance. One can use minutes. So same thing is written again, but it is based on K-means. Now here you have agglomerative, you have divisive, you have n number of clusters. Basically, you merge them or you split them again till you get the you find the ground truth if your termination condition has been reached or not. This is generally less computationally intensive, therefore it is preferred with the larger datasets. Whereas for this case, you have to arrange the clusters into natural hierarchy. What about computation? I guess they have not talked about it, but we just saw for computation for hierarchical one that if you cannot correct for it, and if you cannot correct, it's computationally less intensive. But if you can't, and if you have a bigger network or bigger loop or bigger data to for it to run on, then it might become computationally intensive in that case. Okay. Okay, for this case, it will exactly consider as one set if you have some overlapping or non-overlapping subset. So it will consider one as independent one. Whereas in this case, it is a subset or a set of nested clusters, which are then organized as a tree, as like what we saw previously. It will take one as something like this, and it will start separating techniques as like the things into different kind of branches like that. Okay, so this is how your unnested cluster and nested cluster will look. So here is like, this is what you're looking at is your dendrogram. This branch is what you're looking at is the dendrogram here. So there's your one point, another point, another point, this one, this one, this one. So based on these points, based on the method that you follow for this nested clustering, there are some decision tree making rules that we'll see tomorrow, because that's too much and that's not even related. For what you need to understand how it's being done, that's it. After that, you have Python and Python libraries. You can just directly go and implement it. Okay. So no need to just there is like go in depth into it. Just understand what's being done is like what's happening, how points are being placed, understand the maths of it. No need to mug it up. That was what I was trying to say. Okay. So here it's fine where the shape of cluster does not work when it is okay. So based on the shape of the cluster, it's also sensitive to it. So if you see over here, this ones, they don't work as well as that of k-means when the shape of the cluster is hyperspherical, whereas for this they say that okay, it works. So supervised learning is always better in a way. What it will do is, like, if you have labels for your data set, it always knows what to compare and what not to. So it will keep on doing things, it will keep on separating and will run the algorithm again and again, see when your condition has been met or not. Whereas in case of unsupervised, where you're only giving number of clusters, it probably does not know how much it would should be and how much it should not. So if your shape of the cluster is also changing, it might also be affected or sensitive to that particular thing. So here probably in the beginning, they consider that it's only a spherical set of clusters that it follows to, but not some hyperspherical structures. Probably would go into a complex geometry then. Okay. So yeah, so when it goes into those kind of things, you can stop at any number, or one may find an appropriate by interpreting the dendrogram that you have with you. So, but in this case, you can just directly input the prior knowledge of the clusters that you want your device to differentiate into. It will do the work for you. Okay. So this was how your k-means is. This is how your hierarchical dendrograms are like. Okay. So advantages, it can handle any kind of distances. In case of k-means, it was only limited to the Euclidean distances or based on the centroidal formulas, but here it isn't. Whereas here is can be applied to any attributes or features. There are no such restrictions for it. Yeah. So this is the thing. When you have a minimum distance, you say it as a single linkage. Where it's complete one, you call it as complete linkage. When it's like average of all of the values, you have an average linkage. So it is very sensitive to outlier, as I said previously. Hence, always start your basic things with this Euclidean one. Sorry, with the single linkage, and do not go further ahead into complete or average. You might say that, okay, this is giving me clusters based on all of the values that I have having. But based on those values, some values would be over here. Here also, some values would be over here. Based on these values, only it's comparing the differences over here. So complete linkages are very sensitive to those part, and followed by it average linkages too. But single linkage will always give you the minimum distance any two clusters are apart. And that's what you need, not more than that. Right? So average kind of technique is less susceptible to noise and outliers, but it is nothing but it is biased towards the globular clusters. Here's where if you have outliers more, it would be affected, and that's why your data would become, or clustering would become more sensitive. Okay, so there are different rules or distances to compute this clusters. So this methods you will see when you will do this in Python. So one such is Watt's distance. In Watt's distance, your metric is like you take a sum of square in between each and every point that is separately different for a cluster. So you make a cluster, take a centroid of it, another cluster centroid of it. So based on this Watt's distance, it will try and differentiate or make all of the clusters different. Another kind of techniques are also there. It's like where you can directly give this distance as your Euclidean, which would give you similar results probably as that of your k-means method. Okay. Yeah, so what they said is nothing but an analog of k-means can also be used to initialize k-means. So from there also you can cross-check and verify your results with k-means. So these are the linkages that you have. Again, same thing over here, similarity. Okay, that's it. So after that, what will look was any doubts in this particular slides? Shouldn't be, but if you have any doubts, you can ask me. Like, just was pretty straightforward. Any doubts? No doubts. Thank you. Okay. After that, I'll just share a Python script for the same. So here they'll show us that how do you compute this agglomerative clustering. Not needed, but okay. We'll just see how you can make that particular matrix if it's asked in a question or exam for a particular pixel or point. Probably they won't ask you to make an entire matrix, but yeah, you should know how to compute it. So you know how to compute the Euclidean distance, right? If you have a matrix, you do it as x2 minus x1 whole square plus y2 minus y1 whole square. Now, based on that, you try and compute the distances in between all of these points. You'll do 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. Okay. When you're done with that, it's like compute distances for all of them. Now you start with another variable 2, 3, 2, 4, 2, 5, 2, 6, 2, 7. Again 3, 4, 3, 5, 3, 6, 3, 7. Okay. So when you do all of this, you'll do till 6, 7. When you do it till 6, 7, what you see is like this is something like your lower triangular matrix. In a way, you get a diagonal at 0. Yeah, that's good. So in a way, you get a diagonal at 0 and you have all of your variable values over here. Now what these variable values are, this one will show you the distance in between 1 and 2. This shows you distance in between 1 and 3. This shows you the difference in between 1 and 4. Again 1 and 5, 1 and 6 and 1 and 7. Okay, so accordingly you can see or how the distances that you computed accordingly. So again over here, this shows you distance in between 2 and 3, in between 2, 4, between 2, 5. Okay, so now what you do is, first thing you'll do, you take a minimum element that you see. Now this based, it's like just remove this diagonal. Assume this diagonal wasn't there over here. Based on the diagonal, you see what's the minimum value that you can look at. This is a minimum value. This is a minimum value. Apart from it, this is also a minimum value. Based on these three minimum values, the minimum is 0.7. So you consider the 0.7 value. Then what you'll do is like, now where was that 0.7? 0.7 was this like fourth one, right? So now so that 4 is nothing but the distance in between the first point and the fourth point, right? So what we'll do, we'll compute the distances in between this and this. So we'll compare for 2, compare for 3, compare for 4, 5, 6, and 7. Okay, you compare all of them, compute the minimums there. Now you got a different matrix over here. All of the values have been updated for the distances of between 1 and 4. You do it for all. It's like, now you again see where's the minimum here. So now you see the minimum is like 1.1. Now you start for 3, 2. Okay. So here, okay, sorry, 2, 3. So now you have, now again you look, what's the minimum that you have? Probably this is the minimum ones that you have. Oh no, wait. Yeah. So you also have 1.4 here. Now you do it for this value also. So you have for 145. So in a way, you would notice what you are essentially doing, like we are making different clusters. So you're trying and see which particular minimum distance, when you're on distance, take that point, add it into the basket. That's it. Okay. Now we just made it for 145, 145, 2, 3, 6, and 7. Now you see which one is the minimum. Probably 1.7 is the minimum. Now you compute it for this. So now you do your estimations for this too. So you know that, okay, this point lies in our value cluster. When done, now again you see, so 1.8, now you do for 2, 3, 6, and 7. So when you do it for 2, 3, 6, 7, here you get something like this. The last one that is left is this, so it will go essentially into this particular cluster, right? So if you see, okay, this is your entire cluster that you have differentiated now, but eventually if you take all of the values, this entire thing would also become one big cluster. So this is how it is very sensitive to the number of clusters that you keep on adding to, because for it, it's just an algorithm that it will run. It does not care that, okay, what you are trying to solve. So you should be mindful about that what you actually want your data to do. Okay. So I'll just show you how to implement in Python, and then we'll do the assignment for this week and we'll be done. Okay, from where do I share my screen? Okay, I hope my screen is visible. You can see the Python notebook.
No, ma'am.
You cannot? Share screen. Now? Y'all can see my screen?
Yes, ma'am.
Yeah, okay. Thanks. So for doing this clustering and dendrograms in Python, what you need first is the SciPy family. You always know that you need this NumPy family. Pandas is essential if you have a table or a file to read it up. So an Excel file. Plot are always needed. So what we also went through our previous lectures, that when you have a data, try plotting it. Do nothing with the data, but just try and plot it. Okay. So what I just told you, the score for correlation is this one, this cofinite correlation. So there is a score about it. It will tell you how good or how better your clustering had or clustering came out to be. So it gives you that particular value. But in this particular lecture, the instructor hasn't covered it. If needed, I can cover it tomorrow. Okay, I'll just see what the slides has, if they have this score or not. After that, I can do that. Okay, so then these are for different distances. Probably we don't need it for now, this import ones, but this hierarchy, they have just shown that, okay, what all things are there in the distance. So first you directly read your Excel file that you always know how to. So you have a function of read Excel. Then for making a range for your variables, they have, okay, so what we'll do is like, so for your information, I've taken this file from the here. So week 12, if you go into week 12, there's important data fields. In this important data fields, you'll find a drive link. In this drive link, you have this files that instructor has used in the course. Okay. So this is given for all of the weeks wherever he has used some script files, if you see. So those Excel files have been given for you to solve. Okay. So you run it, you see the table. Now, when you see the table, you see that, okay, there are values from 0 to 6. Now, we all know that in Python, from what the value starts from? Value starts from 0, it does not start from 1. Okay. So then I made a range of 1 to 8. What it will give me? It will give me from till 7, because last one is always n minus 1. Again, everything, so it will give me like 7 values. Now everything is starting from 0. So it would be like 0 to 6. Okay. I hope that was clear. So if you see, wait, it just printed it.
PPT is not coming.
Yeah, I'm not sharing my PPT. I'm sharing Visual Studio Code script.
You are unable to see.
Sorry. Okay.
Nothing is coming. Only JP is there.
Only what is there?
JP.
Oh, can others see my screen? Wait, I'll start re-sharing again. Can you see the screen now?
Yes, ma'am. Now only it is visible.
Previously, it was not visible. Okay. Oh, okay. We'll just start from scratch again. It's fine. So whenever you have to do kind of analysis, first, you need to import this NumPy. NumPy is crucial for all of the libraries. Then Pandas, because if you're handling the data files or something, or you have some Excel files to lead with. Then you have Matplotlib, which will help you plot your data. So these three are like essential and must that you always should import. So without asking, directly import all of them. Then you have SciPy, which will have all of your statistical tools, or it will have or all scientific libraries or something like that. So you'll import that also. Now I took this hierarchical clustering from this particular website. It's like if you go into week 12, you have something as important data files here. In important data files, you have this, which will lead you to this drive link. In the drive link, you have the Excel files saved over here. Okay. Now we just printed that particular thing. You get this variable and you have some index over here. Now for Python, you all know that it starts from 0, what we previously also saw. So I'll make a range of 1 to 8. Now 1 to 8 will always have 7 elements because it's like n minus 1, and it will start from 0. So it's like 0 to 6. Okay, cool with this point. Then we gave our x value as variable 1, y value as nothing but variable 2. You just run that cell. We'll just try and plot it. Okay. Now, after plotting it, we saw this. Now, you might see there are some numbers based on top of this blue balls or blue circles. So what you see there, what it is nothing but now we have tagged our data with certain values. So that value is nothing but our index number that it was. So that is why we made this n. So based on this, for every value, what we'll do is like based on our data, it will see that, okay, is it belonging to 0? Is it belonging to 1 and all? It's just tagging my data with it. Okay, so it just tagged my data to tell me that, okay, which particular value that index was. Okay, when it did, now what I want to do, I want to classify it, or I want to make a cluster out of it. Okay, so for that, from SciPy, from SciPy.hierarchy, I'll import the dendrogram and the linkage that we just saw now. Now for linkage, I'm using single linkage. What it means, it will just see the minimum distance in between these 2 points. That is nothing but the first point that it will come and interact with. I'll give the label to it. I'll make the dendrogram. So dendrogram, I'll pass it. So this is nothing but a kind of figure that it will create. You pass on the method as linked, and that linked has a linkage of single. Give a orientation of top. So the approach that it will follow is nothing but top to bottom. Now what top to bottom had, it will consider everything as one and it will start splitting things into. Okay. So what this kind of approach was called, was it agglomerative or divisive? We just saw now. What was this approach called? Is it agglomerative or divisive? Top to bottom approach. So you have everything into one and then you start splitting things down. Anyone? Okay. So I guess you'll have to go through the lectures again. So agglomerative was the one which is like bottoms up approach where you have everything, you have one values and you try merging them up. Whereas divisive was like top-down approach where you consider everything as one unit and then you try split it. So this top represents, it will start from top and it will start splitting your things into. So it is nothing but your divisive approach. Okay. It will do it descending way. So it will start on seeing that what's the maximum distance to the minimum distance. Okay. So that's it. And you plot it here. Now here, this horizontal line I've just made to show that, okay, this way it will start. So this is your top-down approach. Let's see if I can do it. If there is some method to bottom or something. I don't know if this will, yeah. See, so what now it has done, it will consider all of the units as, sorry, all objects as independent units. Based on that, it will try clustering all of them or making a group of them. But what you see is it's essentially the same thing what it's doing. So that's why it's better, always better to see it in top to down approach rather than prefer to a bottom down approach, bottom top approach. Okay. So then if you want to see that, okay, how your agglomerative clustering will affect it, what's agglomerative here? It's your bottom up approach. What is your bottom up approach? You'll consider everything as one unit and you'll start on making groups out of it, right? So what we just saw you when we did bottom. So based on it, we'll consider the metric or the distance in between them as Euclidean. The linkage will give us single. We try and fit your data. So it will acknowledge me that, okay, it has done agglomerative clustering. First, it has considered 3 clusters to differentiate. So because of that, I gave here k equals to 3, which I passed through this particular variable that is in cluster as k. Now I'm trying to predict the data variable. It will give me something as, okay, let's first do it for k equals to 2. That will be easy for you to understand. Okay, I do it like this. So when I do it like this, what it will give me? It will give me basically 2 variables. One is 0, another is 1. Based on the 0 and 1, if I try and plot it, it will show me that, okay, there are these 2 clusters which are being formed. How did I do that? I just made a scatter plot out of it. When I made a scatter plot, I annotated it with the values of the variables that my labels had previously. So these labels that we predicted using our agglomerative clustering, we just passed in here. So we gave it to the scatter plot. So Python has all of the flexibilities for you to do this. So you no longer need to create another function so that it fits into this particular part. You can directly do that. But let's say if I'm making something as k equals to 3 or 4, let's say 3, a easier one, number of clusters. So what it will do as 0, 1, and 2. If you have more further ones, it will do is like, it will go in higher ways. Okay. Now, if you see over here, this point didn't even make sense to make it as a third cluster. But based on that we gave it that, okay, I want 3 clusters. So it has differentiated and has given that, okay, one is this cluster, another one is this cluster, another one is this point. Now let's say if I just try and change the order of the variables also, this would be highly affected by it. So if I say I'll do like 7 number point is my 6 number point and 6 is my 7 number point, I just change the order of both of them. Now that way also it would be affected based on the distances, how it's been plotting them. So how this clustering is taking them. So this approach is very sensitive towards the number of clusters, your order of the data types that you have. Okay. So that's it. I just have one more basic things to share for classification. So we'll just look at it. So there is another thing that is called as CART. Okay. That stands for your classification and regression. So this classification and regression trees. So what we had seen till now was nothing but everything about clustering. Okay. I might say that, okay, all of them are same. We are doing clustering for all of them, classification for all of them. Well, it is not. What the difference is, for one case, okay, wait. Okay. So clustering, you can do based on your supervised, unsupervised approach, based on your partitioning, hierarchical, all of those approaches, right? So there, your data, everything, no longer to consider them. You can just directly go and differentiate. Again, the data size and all shouldn't matter that much there. But when it's about classification and regression, there's another form that one will tell you how your data is, how different it's important, and how it's like important it is to predict the trends for it. So classification follows for your categorical variables, whereas this regression Here it is used to predict things about, or okay, yeah, here. So it is done for numerical or continuous predictions. So one is categorical, that is like, let's say if you have suggested some classes for two different things. So that is like one or two, two or three, something, or ranking based on the things. So that is discrete unordered label. So that can be done by classification. Whereas the another thing which is regression, so that is nothing but your numerical or continuous prediction, where you have some things from the past, and based on the past you are trying to make some prediction on the output variables. So that is something your regression analysis, where you know the ground truth, and based on the ground truth you are trying to see or foresee into the future that what different values can it be, or you're trying to predict in between the values. Okay, so based on that they have given these examples, only few terminologies here. So there are some things which are called as root node, one is internal node, another one is child node. Always remember, from where the thing starts is your parent node. Okay, so from this, the things and everything, the cause and effect, everything started from. So this is your root node or your parent node. Where it ended, the child born, and when the child got born or whatever, if the conclusion is, you have the conclusion with you, so that's your child node. Okay, after the child node, in between, if you have something. So here, if you see, there's only a parent node, this is your child node. But if you see in between both of them, that is nothing but it's named as internal node that lies in between both of them, or represents an attribute of your parent node, which can have some input information on your child node, so which would give some value to your child node based on that. Okay, so that is where your internal node plays a leaf into, whereas it's not a proper leaf node, as in your, what you have is nothing but this would be a branch and this would be your leaf falling coming out of it, whereas here it's just an internal thing that's coming into, which only plays role to give attributes to your from your parent to the child. Okay, like that. So then there are this decision tree. You have this cart as nothing but classification and regression, where we just saw that okay, you know the things. When it comes that you always know things about, it is always your supervised learning approach. You know about them, what you have to do, how they are being done. You know, okay, you just know, okay, that which, okay, how do I say? Okay, let's say that I know different groups of people. One group of people who have ice cream, another group who haven't had ice cream. I just want to check their blood glucose level or something, and let's say I this data is known to me, but I want to see that how significant, or let's say how different these two groups are, or how their blood glucose level differ from each other. One can be, I would do this t-test and significance test, normality test, and all of those to check how significant the data set is. Another can be, I would like to see that how it's like how goodly, oh, sorry, goodly not, how betterly I can differentiate in between these two classes, or how, or can I do a classification there, can I do a clustering there, or can I do regression there? Can I see that if they are different or not in that approach, if they are lying at one particular cluster or not? So in that way, I know the people, I know what they have had. So I'm just trying to see that what what should I interpret from the values that I have with me. So based on it, everything comes supervised. Now you have the labels, you know your data, you just need to fit into something, and you want to get an interpretation out from it. You want to make an inference about the population there. So hence everything is supervised. Don't ever think that okay, this thing I didn't knew number of clusters based on my problem, I gave the cluster to it, hence it is unsupervised. No, it's not unsupervised. That way dendrograms can once be considered, but again you are doing the cluster, giving an n number of clusters, in some way it's also supervised. So everything, if you consider, is supervised in a way, because you are giving some input to the model, it's not determining everything on its own. So whenever your inputs are being involved, it's something that is supervised. Okay, and this is a greedy approach. Why greedy approach? You won't have any backtracking, but you always want that everything should be very good, your discrimination should be very great, you should see your prediction values very nicely, your accuracy should be very higher. So this is like, you'll tune in the model, or you'll tune in your data accordingly, so that it fits into this classification and regression technique, so that you can differentiate in between your data. Okay, and again, it's very interpretable. You'll see different clusters, you will see different scores for it, so you can interpret them accordingly. So here people have started making a decision tree. So for them, one of this model is called as Gini index. This Gini index is for binary, where one is 0, another is 1, or when one has something, another does not have something, like that. You have different variables here. One is information gain, and another is gain ratio. So there is this thing to make a decision tree. I don't feel that it's that important, but just to give you a glimpse. So first you have a node. Based on node, you have all the features in that particular node. You see if there are features. If there are no features, that condition is terminated. Now you come to the attributes. That is your point number 4. Yeah. So based on the point 4, you'll see if there are any attributes or features in that particular node that you have defined. So that is nothing but your tuple. Tuple is nothing but thing that you cannot change, but it's a list that is immutable, right? So now you go into it. Let's say if you do not have, that is again terminated. So you're done with your all algorithm, your clustering is being done. But if you do have, so based on those attributes, now you'll split your variables. Now comes your agglomerative or divisive approach. Now you do that differentiation based, so that is here no longer everything is continuous. It was nothing but discrete. It will split it, yeah, whether it's yes or no. So it's nothing but a complementary approach now. Till the point you see that your attributes are there, till the point you see there are features in your model, it will try and differentiate things into. It will try and make the branches again and again. If it has not, condition will end, the model will terminate, and your decision is done. Okay. So that's how this entire thing is. So you just make a decision. So this is something that is, they call it as decision tree. It's written in a more formal way here. So you can read up these points. I personally feel that's not at all needed, but you should at least know it how it's being done. So what are the key features there? What are the importance? Why do you have a list, tuple? Why do you looking into the attributes? So when you do for your model, you should know the variables by yourself. Okay. So this was your termination condition. So they have just written it again and again. Yeah. So there are these three attribute measures. One is gain, another is ratio. This is Gini index. So for all of them, you have different formulas to compute them. One is nothing but entropy. Now, if they have it here, I can tell you. Yeah. So this is your entropy. What this tells you, the randomness in your model or the uncertainty of your data set, the information that you're getting back. So how different, or I can say how is like, if everything is belonging to one category or not, if it has some impurity, it won't lie to, and it would make a different cluster out of it. That is what is the physical significance of information, what you have in your data set, or the entropy that you have. How do you compute entropy? Is nothing but something like this. You have your probability variables, you take log bit 2, log base 2. Why log base 2? Because nothing but all information is coded in bits and bytes. So here you have base 2, so it's bits. And you take again log base 2 of your probability. That's it. You have a negative sign out here for probability, this entropy, because that's something considered as a loss of your model. Okay. Again, what you do is like you compute the information here. So that formula is something like this. So here the information, you have an input to your model and you multiply it by your entropy that you had previously. And this gain is nothing but the difference in between both of them. Now gain has something that the smaller the expected information, what you're trying to expect, what you know that it should come, that is required, the smaller thing is the greater the purity of your partition. So if you see that, okay, there is a minimal difference in between both of them, through this minimum value, I can get the true value of my nature of the data set, and that's the greatest purity of your partition. If not, that is not working well. You skip it, do something else. This thing won't work for you, or your data set does not make sense for that particular model that you're trying to do. Something like that. Okay. So based on those, you have this Gini index that is nothing but 1 minus summation of your probability values. You compute it for all these classes. So once it's one told you, the gain told you about the purity of your partition data set. Now here this Gini index is telling you about the impurity of your data set. So how impure your data sets are likely to be. So this is nothing but in between two values, binary values, right? To compute it as 0 or 1. If you have more than that, if you are doing a binary split, you do it for like this. So one which does not have, one which do have. Okay. That's it. After that, the things which are there, in order to learn, like there's something as pruning. We'll look at it tomorrow. It's also for outliers only. And if you see how a node has been fully grown, so after that, what do you do for that grown? So I don't think so it's needed for you to solve this assignment. So you can do this assignment without that also. Okay, if you guys have any doubt, you can let me know, or else we can go to the assignment. If you had no doubts in the script that we just saw, the Python script, you can also let me know. I'll share all of these files in the Drive link, and tomorrow probably we'll go through all of the Python examples, the scripts or the functions that we have looked till now, so that it's all fresh to you before the exam. Okay, any doubts? Any doubts? If you have no further doubts, then we can go ahead with the assignment then. Okay. Now the screen is visible. Yeah, it is. Okay. Okay. Yeah, yes. So let's start from the first question. Which clustering algorithm works well when the shape of the clusters is hyperspherical? So we saw this exact specific words when it would not follow or where it would follow. So which clustering algorithm will work when the shape of cluster is hyperspherical? Well, you can answer this question.
K-means?
Yeah, yes, exactly. K-means will solve you even if it's hyperspherical, whereas agglomerative clustering won't because it's only confined till spherical clusters. Okay. And decision tree, an internal node represents what? We just did it now. Based on your what thing it checks based in between your parent and child node, what it represents and what it checks on. Is it a
Attribute?
test? Yeah, exactly. A test on your attribute. Choose the correct statement about the cart model. So what is a cart approach? Is it unsupervised, supervised, or a greedy approach? So till now what you had was numerically, you have to compute things. Now what you have is everything based on your intuitions.
Supervised. No.
Sorry?
Supervised. Yeah,
Yeah, yes. So it's a supervised technique and it's also a greedy approach. So the answer is both B and C. Okay. Yeah. Next, which library is used to build a decision tree model? So we didn't see that perhaps, but last time I just told you that, okay, if it's a library or a function, you'll have underscore there. But for this particular question, it's not. So the answer for this is decision tree classifier. Okay. So classify the library is something like that. Okay. Gini index enforces the resulting tree to have multi-way splits. Is it true? How many splits is does? Or for how many splits this Gini index gives you values for? What its underlying assumption that everything is? Right? So what would be the answer here?
false.
Yeah, exactly. It's false. So chance nodes are represented by, oh, I guess we didn't see this, but these are like the nodes that begin. So when you start on something, your nodes are always represented by circles. There's also one more question, I guess. When you end, your nodes are represented by triangles. So this is something that you follow here in I guess that distance decision trees. We'll look at it tomorrow. Okay, here. Dash is a measure of uncertainty of a random variable. It will characterize the impurity of an arbitrary collection of examples. So first look at this uncertainty of a random variable. Don't just directly go into impurity and purity because that will give you something else as an answer. Okay. So what's first thing? Uncertainty of a random variable. The very first measure that we look for measuring this data
Entropy.
measures. Exactly. Okay. Decision tree learners may create some bias trees if classes dominate. What's the solution for it? So we'll balance it, imbalance it, balance it after fitting, prior to fitting, after above. So we did something as standardization, remember? Where before doing something to dataset, we'll standardize it. But after that, what you have, the output values are no longer effective. So here in this case, what do we do? If some classes are dominating, probably we can normalize everything up. So that is something as
Balance the data set.
exactly. What we'll do is like we can balance the data set prior to the fitting so that if you have everything on same lines, everyone is on the same base, and now you start on doing your classification or clustering. Last question. Suppose your target variable is the price of a house using a decision tree. Which type of tree do you need to see the keyword to predict the target variable? Someone's trying to say something? I guess Sham was trying to say something, but sorry, you weren't audible. Someone else?
Regression tree?
Yeah, yes, exactly. So it's a regression tree where you try and try to predict based on the past values that you have. So I guess that's it for today. If you have any questions, you can stay back and let me know. Thanks for joining.
Thank you.
Thank you.
Thank you, madam.
Thank you.
Thank you.
Thank you. Okay, so if there are no further doubts, I'll end the session. See you tomorrow. Thank you.